Welcome back to the VeraGrid Feature Spotlight series. Today, we're tackling the optimal power flow, or OPF for short. It's one of the core tools behind everything from day-ahead market clearing to operational and transmission planning studies. In simple terms, the OPF helps us answer a practical question. Given the grid we have now, how can we meet demand at the lowest cost while keeping the system secure and within technical limits? The DC optimal power flow remains the standard formulation in most cases. Very similar to the conventional power flow, it simplifies the network equations by fixing voltage magnitudes to 1 per unit and focusing only on active power and phase angles. This turns the problem into a linear optimization that can be solved efficiently even for very large systems. Each generator is assigned a linear cost term with respect to active power, and the solver finds the generation schedule, which means total demand, at minimum cost while keeping line and generator limits within range. In transmission networks, where voltage magnitudes stay nominal and lines are predominantly inductive, this formulation provides a fast and practical approximation of the economic dispatch. It highlights which parts of the network are congested, how generation shifts when constraints appear, and how overall system costs evolve under different scenarios. In VeraGrid, the DCOPF is solved using a mixed integer programming approach. This allows continuous variables, such as power outputs and flows, to be optimized together with discrete operational decisions, like unit commitment or switching states, within the same framework. The MIP solver handles these problems efficiently while maintaining full visibility into the constraint activity and optimal costs. Still, the DC formulation has some known limitations. It ignores reactive power, voltage variation, losses, and transformer tap effects, meaning it can miss situations where these factors become decisive. In practice, engineers often complement a DCOPF with a full AC power flow to confirm that the simplified dispatch remains physically valid. This workflow, DC for speed, AC for validation, remains standard because it combines the computational efficiency with a reliable check. The AC optimal power flow includes the full electrical behavior of the grid. This allows the optimizer to consider both the economic and physical limits of operation in a single step. Each generator has cost functions for active power, and constraints now include voltage bands at each bus, generator reactive limits, transformer tap positions, apparent power limits on lines and transformers. By modeling both the active and reactive effects, the ACOPF provides a more realistic picture of system behavior. It can identify when voltage or reactive constraints become the true bottlenecks. It also captures system losses directly, adjusts tap changers or phase shifters to relieve stress, and evaluates how close the system is to the reactive and voltage limits. In VeraGrid, the ACOPF is solved using a custom-built interior point method that handles the nonlinear equations and inequality constraints simultaneously. The algorithm searches for a feasible minimum cost solution within the full AC domain, enforcing voltage and power limits through barrier functions. In practice, the ACOPF is generally used to verify certain specific scenarios in both long-term and operational planning. Although it's computationally more intensive than the DCOPF, the ACOPF is progressively becoming more practical for routine studies thanks to advances in solver algorithms and the increasing availability of high-performance computing. Now, let's move to the practical demonstration. We'll start by loading a small test network, in this case, the IEEE 14 bus system. Once the grid is open, we'll check a few key parameters in the database to make sure everything is ready for the OPF run. For generators, the most relevant fields are the cost coefficients, cost2, cost, and cost0, which define the quadratic, linear, and fixed parts of the cost curve. You can also specify a startup cost and shutdown cost if you want to include unit commitment logic, and use the enabled dispatch flag to fix or release certain generators during optimization. For loads, the main field is cost to shed, which defines how expensive it is for the solver to disconnect demand, essentially the value of lost load, so that shedding only happens as a last resort when no feasible solution exists. For lines, it's important to set the cost of exceeding rating. This introduces a penalty when a line exceeds its thermal limit, helping the optimizer balance congestion against the overall generation cost. Once these parameters are set, we can open the settings panel. Under the general settings, we can choose the method, the linear OPF for DC analysis and nonlinear OPF for AC study. We also have some additional checkboxes like skip generation limits or add report, which can be used for quick testing or additional documentation. In the linear settings section, we can select the MIPS solver. By default, VeraGrid uses HISE, an open source high performance solver. However, the platform can also integrate with commercial solvers when specific licensing or performance requirements apply. Other options include toggling unit commitment mode for discrete generator scheduling, approximate losses for slightly improved realism in DC mode, fix infeasibilities and retry to automatically relax tight limits if the first attempt fails, to use contingencies during the optimization, and to use generation and load shift keys as costs. In the nonlinear settings, we can configure the ACOPF solver. The IPS method defines the interior pole algorithm, Newton-Raphson by default. Tolerance, iterations, and truss radiates control convergence behavior, while initialize with power flow can obtain a starting point closer to the optimum, and control Q limits options activates the reactive power bounds for generations during the optimization. Now that we've checked all the settings and made sure everything is correct, we're ready to start. We'll start by launching the DCOPF and then look closely at a few key outputs. The first one is the marginal pricing, which indicates how the cost of supplying an extra unit of power changes across the network. We'll then review the voltage angles and branch loadings. Finally, we'll check the generator active power to see how each unit is contributing energy into the system. Once the OPF results are ready, we'll use VeraGrid's built-in option to transfer the dispatch directly into a power flow. This automatically sets an electrical validation run, using the OPF outputs as the starting point. It's a quick way to confirm that the optimized dispatch remained feasible when all electrical details are taken into account. After the validation run, we'll check the updated results again, focusing on any overloads or voltage deviation that appear once losses and reactive effects are included. This will allow the user to make necessary adjustments to the dispatch if the solution is electrically unsound. We've also prepared a script that will allow you to directly compare the OPF and power flow results. For cases with large divergence, or when key studies require it, we can also run the ACOPF to prevent these iterations. Just changing the setting to nonlinear OPF in the Settings tab and running the simulation again, we can see the results now include voltage variations and the inclusion of reactive power in the network. Once again, all of this setup can be automated directly in the Scripting tab for the GUI. That wraps up this feature spotlight. If you have any questions or run into something you'd like clarified, feel free to leave a comment below, check out our documentation, or reach out to us directly on Discord. We're always happy to help. We'd also love to see what you build with VeraGrid, so don't hesitate to share your projects or results with us through the contact links in the description. And finally, if there's a feature you'd like to see added, consider contributing to the project. Your ideas and feedback play a big role in shaping the future of VeraGrid. Thanks for watching, and see you in the next video.